All right. Um, Good afternoon, everyone. Today is our last class in this semester, and um, so in the last class, I want to talk about the common final exam. Okay. Uh, this exam is the last assignment of this course, and the due day, the deadline for the common final exam is next Monday. Okay. Um, the exam question is already available on the Canvas, and you guys can download it. And as usual, after you finish the exam, re-upload it on the Canvas so I can easily grade it. Okay. Um, in today's class, I will go through the common final exam, like exam number 2. I will give you few steps of each question, so you guys have uh, better instructive suggestions to finish the common final exam. Okay. All right. So let's get started. There are 5 questions, as you can see. Excuse me. As you can see, there are 6 questions in the common final exam. The first one is the nodal analysis. Um, the question is use nodal analysis to find IR1 and the power dissipated by R3, right? So the knowledge point that this question is asking, that is nodal analysis, right? All right, so to solve this problem, the first step of using nodal analysis is we need to assign nodes, right? So we can say the bottom line is the ground, and this is node A, this is node B, and this node you don't need to assign an unknown voltage variable because the voltage at this node, node C, VC is 1 volt, right? And you can say the voltage at node A is VA, and the voltage at node B is VB, right? All right, so at node A, you can write the KCL equation, right? There are 3 branches are interacting with node A. 3 amp provided by the current source. IR1 is going down, which is the current on R1. IR2 is the current on R2. You can say the flowing direction is from A to B or is from B to A. It doesn't matter. Okay. And also you need to assign the current on R3, and that is IR3. You can say it's flowing down, and IR4 you can say it's flowing from B to A, or flowing from B to C, or you can say IR4 is flowing from C to B. It doesn't matter, right? What matters is the KCL equation. At node A, the entering current is 3 amp, and the leaving current is IR1 and IR2, right? And at the second node, node B, the entering current is IR2, leaving currents are IR3 and IR4, right? As node C, actually you don't need to write KCL equation for this node, because you already not necessary, right? Because you already know, because VC is 1 volt. You already know the voltage at point C, so you don't need to set up the KCL equation. All right, and then you need to write IR1, IR2, IR3, and IR4 in terms of unknown voltage variables such as VA and VB, right? So IR1 can be represented as VA minus 0 divided by R1, and IR2 is VA minus VB divided by R2, and IR3 is VB minus, VB minus 0 divided by R3, and IR4, that is VB minus VC divided by R4, right? And then you can plug in these four representations back into two KCL equations and solve the value for VA and VB, right? And after you have VA and VB, IR1 can be represented by VA over R1, right? And also you need to find what's the power dissipated by R3. To calculate power, you can use this equation. P equals to I square R, right? And this I is IR3, and this R is R3, correct? Right, so that's the first question. Should be easy to handle, right? Right, second one, use Thevenin's equivalent circuit. Find Thevenin's equivalent circuit to the left of A and B, right? So, in this problem, we need to use Thevenin's theory to find what's the value of IL, and that is the current flowing through RL, right? So to do that, the first step you need to do is you need to remove the load resistor from the circuit, remove it from the circuit, and then point A and point B becomes an open circuit. The voltage between these 2 points is defined as V Thevenin's, right? So let me draw the circuit after you remove the load resistor. Right. So that's the circuit after you remove the load resistor, and AB becomes an open circuit, which means there's no current flowing through point A and B. Alright, and then the voltage between A and B is the same voltage from here to here, right? Because this point is connected to point A, this point is connected to point B. Alright, so how to solve this problem? How to find V Thevenin's, right? V Thevenin's is defined as the voltage between point A and point B. The simplest way to solve this problem is you can use several ways, but the way I think is the easiest or the simplest. Maybe you can use superposition method, right? So let's call it VS1. This is VS2. You can first keep VS1 and remove VS2, and that will give you a new circuit look like this. Since VS2 is a voltage source, so you need to replace the voltage source with a short circuit, right? And this is R1, this is R2, this is R3. 3 ohms, 6 ohms, and 2 ohms, right? And now we need to find what's the voltage between point A and point B. So to do that, you can first combine R2 and R3 because they are connected in a parallel connection. So the overall resistance, you can call it R total. That is the combination of R2 and R3, which equals to 6 times 2 over 6 plus 2. That equals to 12 over 8, right? And that is 4 over 3. 4 over 3 over 2, yes, 1.5. 1.5 ohms. And after you combine R2 and R3, and then we can find what's the current flowing through the RT. IRT equals to 9 volt divided by R1 plus RT, which equals to 9 divided by 3 plus 1.5, and that should be 2 amp, right? And after you find IRT, we can find V Thevenin's dot, which is the voltage between these 2 points. That equals to IRT times RT equals to 2 times 1.5, which is 3 volt, right? So you find V Thevenin's in the first case. And in the second case, we can keep VS2 and remove VS1. So since VS1 is a voltage source, you can replace it with a short circuit. And only VS2 is left. So using the same method, you can find what's the voltage across point A and point B. Right, this is 3 ohms, this is 6 ohms, and this is 2 ohms. So to do that, you can first combine R1 and R2, which give us, we can call it RT2. That's the combination of R1 and R2, since they are connected in a parallel connection. So the overall resistance is going to be 3 times 6 over 3 plus 6. That gives us 2 ohms. And then the voltage, the current flowing through IRT2 is VS2 divided by IR2 plus R3. Because after you combine R2 and R3 as RT2, RT2 is connected in series with R3, right? So that gives us 2 over 2 plus 2, which equals to 0.5 amp. And after we have IRT2, we can find V Thevenin's double dot, which is VAB, that equals to IRT2 times RT2 equals to 2 times 0.5 equals to 1 volt. Okay, so the final step of finding V Thevenin's in the superposition method is we sum V Thevenin's dot and V Thevenin's double dot together, and we got 3 plus 1 equals to 4 volt. Okay, so that's the value of V Thevenin's. But we haven't finished this question yet. We also need to find what's the value of R Thevenin's. And to find R Thevenin's, we need to make all sources 0. There are 2 voltage sources in this question, so we need to replace them with a short circuit. And that's the circuit after we make all sources 0, R1, R2, and R3. And as you can see, these 3 resistors are connected in a parallel connection. So R Thevenin's, which is the overall resistance of the circuit, and that is the 3 resistor connected in a parallel connection. So we can calculate R Thevenin's, right? To do that, you can use the general equation to find 3 parallel overall resistors. That will be R1 to the power of minus 1, R2 to the power of minus 1, plus R3 to the power of minus 1, and together to the power of minus 1, which equals to 1 over 3 plus 1 over 6 plus 1 over 2, together to the power of minus 1. And that equals to, the first one is 6 over 2, the second one is, is 2 over 6, the second one is 1 over 6, and the last one is 3 over 6 to the power of minus 1, which gives us 6 over 5 unit is ohms. 6 over 6 6 over 6, that is 1. So the result is 1 ohms, right? Or after we have V dampness and R dampness, we can draw the dampness equivalent circuit with V dampness, R dampness, and the load resistor, which is 1 ohms. This is 4 volt. This is also 1 ohms. So we can easily find what's the value of IL. That should be V dampness divided by R dampness plus RL, which equals to 4 divided by 1 plus 1. So the final result is 2 amp. Okay. So in this question, I'm using superposition method to find V dampness. Of course, you can use other methods to find V dampness, such as mesh analysis. You can define two mesh currents, IA and IB, and of course, you can use nodal analysis to solve this problem either, right? No matter which method you choose, you should find a same V dampness, which is 4 volt. Okay. The method to find R dampness is limited. There's only one way to find R dampness, and but a key point of finding R dampness is you need to remember to make all sources 0. And in this question, since we have 2 voltage sources, so we replace them with short circuits. Okay. Alright, so that's question number 2. Question number 3, find V naught in the polar flow. Find V naught in polar flow, use mesh analysis. Okay. So this problem is AC circuit, right? We have, but the good thing is, all components are presented in impedance, and sources are presented in the polar flow. So we don't need to find impedance of each component, right? All right. We can use the question access to use mesh analysis, right? So let's define 2 mesh currents, I1 and I2, flowing in the clockwise direction. And let's say this is VR1, this is VR2, this is VR3, and this is VR4. And based on the mesh current direction, VR1 should be positive on the bottom side and negative on the top side. And VR2 is positive on the left, negative on the right. VR3 is positive on the left, negative on the right. And for this one, VR4, positive is on the top side, negative is on the bottom side. Okay, and then we can write the KVL equation. For the first mesh, that should be VR1 plus VR2 plus V naught and minus 2 volt, 20 degrees volt is equivalent to 2, right, as the note here. So that equals to 0. That's the first KVL equation. The second one is positive VR3 plus VR4 minus 1 volt, because 10 degree is equivalent to 1 volt, right? And minus V naught equals to 0, right? That's 2 KVL equations for 2 meshes or for 2 blocks. And then we can represent VR1, VR2, VR3, and VR4 in terms of mesh currents. The first one, VR1, should be R1 times I1. VR2 should be R2 times I1. VR3 should be R3 times I2. VR4 is R4 times I2 either. Okay? And for the last one, V naught, that should be I1 minus I2 times the resistance, the impedance of this capacitor. Let's call it ZC. ZC. Okay. And why is I1 minus I2? Because the polarity of V naught is positive on top side, negative on the bottom side, right? So the current should flowing from top to bottom, which is the same direction with I1, and the opposite direction with I2. Okay, and then we just need to plug in these 5 variables back into 2 KVL equations, and we can solve the value for I1 and I2. After we have I1 and I2, we can use this equation to find what's the value of V naught. Okay, so that's problem number 3. Problem number 4, consider the transient circuit. So this question is asking us about the transient analysis. In the transient analysis, the first step we need to do is to determine which type of circuit it is. For this circuit, for this question, since we have resistor and inductor, so this is a RL circuit. And for RL circuit, we can write the conclusion of transient analysis, which is the current flowing through the inductor follows K1 plus K2 times e to the power of t over tau. This expression, yes, not expression. What I'm saying is this word, expression. Okay. And then we just need to find what's the value for K1, K2, and tau, so we can solve these 3 questions. Okay, K1 is defined as IL positive infinity. K1 plus K2 is IL 0, right? Alright, so let's find IL 0. To find IL positive infinity and IL 0, we need to draw the time axis, right? We're starting from minus infinity and end up with positive infinity. At minus infinity, the circuit is initially built, so IL minus infinity should be 0 amp. And next point is 0 minus, which is just before t equals to 0. When time t equals to 0 minus, the circuit, the switch is still closed. Switch is closed, which means the current can flowing from Vs to the inductor, and since from minus infinity to 0 minus, we have long time to let the inductor being fully charged. So the inductor should be a short circuit at this moment. So the circuit at this moment, we can draw the corresponding circuit. Since the inductor is equivalent to a short circuit, so I use a short circuit to replace the inductor. But we still need to find what's the current flowing through the inductor, which is this branch, right? And the current at this moment is named as IL 0 minus. Okay, so this is 8 volt, this is 1 ohms, this is 3 ohms, and this is 2 ohms, 3 ohms, and 5 ohms. And as you can see in this circuit, with this short circuit, these 3 resistors are shorted out, right? Because comparing to this branch, there's 0 resistance on this branch, so the entire current gonna flow this way instead of go through the other 3 resistors. Alright, so IL 0 minus can be easily calculated, which equals to 8 divided by 1 plus 3 equals to 2 amp, right? And after you have this value, we can find IL 0 plus easily, because the current on inductor cannot be changed rapidly. So IL t equals to 0 plus equals to IL t equals to 0 minus, which equals to 2 amp. Okay. And for the last moment, which is t equals to 0 which is t equals to positive infinity. At this moment, the switch should be opened, and it has been opened for a long time, and which means there's no connection between the inductor and the power supply, and the only components connected to the inductor L is R2, R3, and R5. And it says right now t is positive infinity. From t equals to 0 to t equals to positive infinity, we have been going through a long time, which means the energy stored inside the inductor will be dissipated, will be dissipated, and there's no energy left in the inductor. So the current for the inductor gonna be 0, right? Because there's no external power connected with the inductor. All right, so with this information, we can calculate what's the value for K1. K1 should be IL positive infinity, that is 0 amp. K1 plus K2 equals to 2 amp. So we can find K1 is 0 and K2 is 2. Okay? After we have ILT, we haven't finished the expression of ILT yet, because we still need to find time constant tau, right? To find tau, we need to look at this circuit, because that's the circuit when time t is greater than 0. So there are 3 resistors connected with the inductor, R2, R3, and R5, and they are connected in a series way. So tau equals to L over R. That should be, inductance is 1 ohms. R should be the overall resistance of R2, R3, and R5, and that should be a series combination. So we just need to sum them together. That should be 2 plus 3 plus 5, which equals to 1 over 10. Okay, so that's the value for time constant tau. The unit is second. So now we can say we finally find the expression of ILT. That should be K1 is 0 plus K2 is 2 times e to the power minus t over tau, which equals to 2 times e to the power minus 10t. Unit is amp. And after we have ILT, we can find VR2, right? Because VR2 equals to ILT times R2. And ILT is 2 times e to the power minus 10t. R2 is 2 ohms, so the final result is 4 times e to the power minus 10t. Unit is volt. Okay? Alright, so that's question number 4. Question number 5, digital circuits. Oh, and question number 6. The last 2 questions are about digital circuits. So for this one, convert decimal number 125.25 to binary, right? So for this one, this question is very similar to homework 6, question 1. You need to divide this number into 2 parts, the integer part and the fraction part. For integer part 125, you need to use the repeatedly division by 2. Repeated division by 2 to find the the binary representation. And for 0.25, you need to use the successive multiplication by 2 to find the binary representation, right? And then you just need to combine them together. And the second question, B, convert minus 10 to 8-bit signed binary number to use complementary format. So to find minus 10, a negative decimal number in the binary form, you first need to find what's the positive 10, right, in the binary form. And then flip the bits and and then you need to plus 1 with the flippy bits, and that's the 2's complementary format of a negative decimal number. But you will find this number is actually a 5-bit binary number, which is not 8-bit binary number. So what you need to do is you need to use the sign extension to add 3 ones in front of the original 5-bit binary number from an 8-bit binary number, right? Should also be very easy to do. Okay, this one do the summation of below 6-bit signed binary number. So it's a signed binary number. Okay, the first bit is representing -1. Convert both numbers and sum to decimal. Indicate if there is an overflow. So the first binary number in the decimal form, be careful because this is a signed binary number, right? So the first digit 1 is representing -1. So to find, I do the first one as the example, and you guys can do the left. So 1 0 1 0 0 1. First we need to count positions, right? Starting from right to left, and starting from 0. So the position should be 0 1 2 3 4 5, right? And then we can decode this binary number. Since it's a signed binary number, the first digit is representing -1 times 2 to the power 5 plus 1 times 2 to the power 3 plus 1 times 2 to the power 0, right? And that equals to -32 plus 8 plus 1, which equals to -23, right? So that's the decimal representation of this signed binary number. And you can do this step for the second signed binary number using the same method. And then you can sum them in the binary form and also sum them in the decimal form to tell whether or not it has the overflow. The method is you need to compile the final result and these two summary numbers. If the final result is longer than these two summation numbers, then you have an overflow. Otherwise, there's no overflow. Okay. All right. The final question for the following function, find the minimum sum of product expiration. Show the kernel map. Right. So to do that, you need the 4-input kernel map. 0 0 0 1 1 1 and 1 0. 0 0 0 1 1 1 and 1 0, right? And then fill the numbers in the cells. 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15. And then fill ones according to the SOP function. So in this SOP function, cell 0 is 1, cell 1 is 1, cell 2 is 1, cell 3 is 1, cell 5 is 1, cell 8 is 1, cell 10 is 1, and cell 12 is 1. I'm sorry, cell 12, this one, right? There's a tricky point I want to emphasize, which is there's a tricky point of circling I want to emphasize, which is for these 4 corners. These 4 corners can be circled as a single cell because all boundaries are adjacent, right? So these 4 corners can form a 4-cell circle. Okay, that's the point I want to emphasize. And then you can circle these 4 vertical ones as a single one, right? And let me see if yes, that should be right. And then for these 2, you can circle them together, and these 2 you can circle them together, right? That's how we do the circling for this question. And then you need to translate each circle as a SOP, as a sum of product expiration. The method is to find unchanged variable, right? And then you just need to sum them together to find the final result. Okay. All right. For the last one, you need to use the De Morgan's law. When you have a plus b bar, you need to change it to a bar times b bar. Break the line, change the sign, right? So if you break the line here, you can change the sign as a times b bar times a plus c bar, right? Plus, and also you can break the line here, c bar times b plus a bar m bar. And then you can break the line here, and we got a times b bar times, I'm sorry, that should be a summation, right? Because break the line here, the original multiplication becomes a summation. And then break the line here, original sign is summation, change that to multiplication. Plus c bar times break the line here. And we got the same thing here, that should be plus, right? Because we break the line here, original sign is multiplication. Here it becomes summation. And then we break the line here, and we got b bar times a double bar, right? And that equals to a times b bar sum a bar c bar plus c bar plus b bar times a. A double bar is a. And that equals to a b bar plus a times a bar is 0. So this term is gone. Plus c bar plus a b bar. And here we have 2ab bar, right? A plus a is a. So we got a b bar plus c bar. So that's the final expression of the original expression. Okay, alright, so that's the common final exam. The overall difficulty level of the common final exam, I think, it's not very hard. It's not very difficult for you guys to finish. And you guys have 1 week to finish the whole common final exam, and after you finish that, re-upload it on the Canvas. And also, I'm not very sure about the grading, the final grading system. Right now, there are 2 options for you guys. The first one is the conventional grading method, which is ABCD method, right? If your final overall grade is over 90 degrees, then you have an A in the class. If you are located if your grade is located in 80 to 90, then you get a B. 70 to 80 is C, and so on and so forth. But there's another option you can choose, which is the fail and pass grading system. So when if you choose that way, then you will have a pass of this course if your final grade is over 60 points. And you will fail of the class if you get below 60 points. Okay, so but right now I'm not sure how you can choose how you can choose and how to reflect your selection on your final grade. So I'm still I will figure it out before the final day of posting your grade. And please check the Canvas announcement regularly, because I will post the final grading system, the method, on the Canvas. So please keep tracking the updates on the Canvas. Okay. And as usual, if you have any questions, please let me know. And this is our final class for this semester. So good luck for the final exam, and good luck for the remaining semester, and stay healthy. Okay. All right. I see you guys. If you have any questions.